All right, folks. Well, I want to continue on with our talk about code generation. I want to get into a little bit of a couple of different data types that might have some interesting points for us to look at, and just thinking about what we have to do in terms of code generation for them. So we'll start off with arrays, and then maybe do structs and unions, and a little bit of pointers, and a few other bits and pieces, and see where we get to. So there's the plan. Okay, so if we start off with arrays, again, let's think about what we need to do in terms of code and kind of at the assembly language level to go through and start accessing the individual array elements. So we'll look at it as sort of random access at first, and then we'll get into sequential access where you're going through, all of a row or all of an array in sequence. So one of the things, so we'll start with one-dimensional arrays, random access. The arrays themselves, in theory, the indexing can begin at any number we want. All right. Usually we talk about array indices starting at 0 or 1, right? We're used to the sort of C-ish idea of array indices start at 0. But, really, there's no real reason why you couldn't say, well, our arrays start at position 3, or, the first index is position 3, the first storage cell is position 3. Depending on the nature of your language, there might actually be a reason for that. I can't think of one off the top of my head, but 0 or 1 are pretty common. So I'm going to refer to that base address, that base index, as our B. And the idea is that if we've got an array of n elements, so B's the first one, and we have n minus 1 of them after that, and they've each got a fixed size S, so think of that in terms of our bytes or whatever your storage unit happens to be. Then if we want to compute the offset from the start of the array to the ith element, it's whatever the index position is minus that starting base index, and then multiply by the size, right? Nice and straightforward. And if b is 0, then this is just I times your size, which is actually one of the big reasons why array indices tend to begin at 0, because then you don't have to do this step. So if we were going to look at that in terms of sort of a pseudo-assembly language, if we want to get at array element I, and we've got some fixed known base index, let's call it 1 just so it's not 0 for some experimentation here, and we've got some fixed size element, so let's say they're 8-byte elements, then we want to go through, load the address of our array into a register, load the content of our index variable into another register. We want to subtract that base from the index, so in this case that's just the 1. We want to multiply by the size, so in this case that's the 8 bytes per element. And then we want to take that offset that we just calculated, right here we've got our offset, there we've got our base, add them together, and we get the address of whatever our destination is going to be, and then we can load that, or the content of that, whatever's at that address, into our desired register, so we can actually play with whatever array of I happens to be, or array element I happens to be. So there are a fair few steps to go through there. Now, if we're lucky, and we're following this idea that things are kept in registers a lot, then maybe the array address is already in a register someplace, and maybe our index variable I is already in a register someplace. So for a specific individual access, we wouldn't have to do that. That would hopefully have been taken care of by some earlier step. So we're just going through, subtracting our base, doing our multiplication to get the size, and adding it in, and going off to memory and grabbing the actual beastie. So there's one possibility. Now again, we can improve this a little bit. So again, if we're using a base index of 0, then we don't have to do that subtraction step. The multiplications tend to be pretty slow, but if you're going through and multiplying by a power of 2, then you can do bit shifts instead. So since we were multiplying by 8 that time, maybe we'll just do a bit shift of 3, and again, that's going to be a much more efficient operation. And quite a few assembly languages provide us with a way to take a base address and an offset, add them together, and grab whatever's there. So if we assume that we've got an instruction along those lines to take the two addresses, add them together, grab what's in memory and put it there, then we can at least speed this up a little bit. And again, if we're kind of assuming that the loading the array address only happens to be done once the early on in the process, and the loading of our index register, assuming our index variable is already in a register someplace, then most of our individual accesses are looking something like this. All right, do a shift and do a load. So that's actually not too bad as far as things go. Now, if we go from there to sequential access, we can go through and say, well, if we think of our array elements as all being stored kind of contiguously in memory, so they're all in sequence in memory someplace, and you've got this loop that's going through and doing something with each successive element, then back at the beginning, we have to compute the address of that first element. But for each subsequent one, we know it's going to be right after the one that we're working on now. So we just take the size, add that to our offset, and go load whatever that next element is. So for each subsequent operation, right, for after that first one, for each subsequent one, you're just going through and saying, okay, well, add 8 or whatever the size is and load. Add 8 and load. Add 8 and load. So again, you can get more efficient access set up if you think about the way things are arranged. So if we take that one step further and think about multidimensional access, so now let's say we've got a bunch of rows and a bunch of columns, and let's say we're going to start at row M and we're going to go to row N, and for each row we're going to go from column A to column B. So we're doing some chunk kind of in the midst of the array, but we are doing a bunch of rows in sequence and we're doing a bunch of columns in sequence. So for that, again, we can go through at the beginning and figure out where the first thing is that we're going to access. So we go through and find out where row M, column A is, figure out the address of that one first. Now, while we're going through an individual row, we can just use our add 8 or whatever the size is trick to go through and grab the next one, the next one, the next one, the next one as we go through this. Then when we want to jump to the start of the next row or to the position A in the next row, if we know how big the size of the total size of the array row is, so the number of elements times the number of elements in a row times the size of an element, then we know how far from the beginning of one row to the beginning of the next. So we could also set things up so that, after each element, we just add the size of the element, and then at the end of a row, we add whatever's necessary to get to the start of the next row. So we're doing just one more add operation. So this way we can get, again, a much more effective way to iterate through our array, assuming that it's stored in row major order. So we've got all of row 0, and then all of row 1, and then all of row 2, and then all of row 3, all stored in sequence somewhere in memory. And we can come up with a reasonably effective way to do this. Now, if we don't have that, let's assume that each row is stored all in sequence in memory someplace, but you might not have all of them back to back to back to back to back. So we might have row 0 someplace in memory, and row 1 someplace else, and row 2 someplace else, and row 3 someplace else. Then what we might do is add an extra indirection vector at the start. So the kind of outer layer of the array, if you like, is a one-dimensional array of pointers where each one of them gives you the pointer to the start of one of the rows. So array element I points to the start of the ith row. And so array element, ij says, okay, follow that pointer to get to the ith row, and then use j as the index into that row. So you've got extra space that you're using for that kind of outer row of pointers, or that outer array of pointers, but your rows no longer need to be arranged contiguously in memory. But of course that messes up the algorithm we were just using, where we assume that all we have to do is add the size of a row and jump to the right spot in the next row. So if we're doing something like that, then what we want to do is say, okay, well, let's load the address of that indirection vector into a register someplace, follow that to get the address of the first row, and then repeatedly what we'll do is say, okay, let's go through our row normally, right, doing our get the address of the first element, and then each time through add 8 or whatever it happens to be. And when we hit the end of the row, or the portion of the row that we're interested in, then add 8 to the address that we loaded in our 0 here to go through and say, okay, well, what we want to do is now move on to the pointer for the start of the next row. So you're adding the size of a pointer to that array, or to that address, so that you can just jump to the pointer to the start of the next row. So again, you can find ways to make this reasonably efficient even with something like this. Now it's still obviously slower than the approach we were suggesting the first way through, where everything's stored contiguously, but it's still not that bad. All right, what else have we got for arrays? Arrays as parameters. Now, usually you're going to pass them as an address. Again, for the most part, you don't do a full deep copy of an array when you're going to pass it as a parameter. Even if you have to take some extra steps of, the compiler sticking in a flag saying don't modify anything that you get at through this particular pointer. But you can go through and say, okay, let's just pass the address of the array, and then the call E can do whatever it wants with it. But if it's a multidimensional array, or if you want to be able to do bounds checking, then the callee needs to know the dimension sizes, how many rows there are. What's the size of each dimension? How many rows, how many columns, so that it can figure out where, the ith element is in row whatever. Now, it's possible that stuff isn't known at compile time. So at compile time, you can't stick in the right instructions to actually jump to the right spot, the right calculations to jump there. You have to stick in the code or some mechanism that's going to allow it to figure out how big an array was actually passed and what the dimensions of that array were. So one of the ideas is to go through and, ideally we'd still like to set it up so that all you're doing is passing a pointer more or less. But one of the things that the compiler can do is say, okay, well, what I'll do is somewhere off in the heap, I'll generate a description of the array dimensions, a struct or whatever it happens to be, with the assorted, how many dimensions there are and then what each of them are. And then the compiler can pass a pointer to that descriptor as the parameter to the function. So the function gets this pointer to something off in memory that's got the information about the array itself, including in all likelihood a pointer to the actual array content. So this is not unusual. You might hear that pointer to the descriptor that gets passed as a dope vector. And again, it means that in the callee, you have to have the extra code to go through and follow the pointer to the descriptor, get the dimensions, get the pointer to the actual array content, and work from there. But again, it's all things that can be done to make this reasonably seamless when we actually have to execute this. Character arrays. Again, for the most part, we can treat these just as regular arrays, just small element sizes. Maybe it's just 1 byte elements. There's a couple of unusual things associated with them just because of the way character arrays tend to get used as text holders. Right? You've often got this idea that you'll create an array that's bigger than you actually need, and you'll use some contiguous chunk at the front of it. You'll read somebody's name into the front, or you'll put some message in the front. So in that case, you've got to have some way to know how big the array as a whole is, and some way to figure out where the current end is. And so there's a couple of ways of marking where the current end is, either the null terminator, right, the C style, or the sort of Pascal style where you store the current size as an integer at the very front of it. Maybe you think of it as a struct where you've got this size field and then the character array. The access to the individual elements within it are pretty much the same as our traditional array discussion so far, with maybe one small proviso. What if the architecture, the assembly language that you're working with, has, a fixed smallest addressable size, a fixed smallest size you can move. What if that doesn't go down as small as whatever characters you're trying to represent in your language? Right? So maybe the smallest addressable unit is, 2 bytes, for instance, and your chars are 1 byte. Then what do? Then you have to be able to go through, and if you're trying to store your chars contiguously so you're not wasting space, then in each addressable unit, you've got 2 chars. And so when you want to grab one of them, you have to know whether it's going to be the odd one or the even one, if you like. And you're going to have to use something like bit masks to go through and get the specific content that you want out of it. So there are, once in a while, some quirks to worry about. And I guess some of the operations that you tend to perform with character arrays might also be a little bit problematic. If you think of things like concatenation, it's pretty normal in string operations, in text operations, where if you say concatenate A and B, you could either mean take A and glue B onto the end of it, or glue a copy of B onto the end of it, or you could mean create a new string whose contents are a copy of A followed by a copy of B. So for the first one, it's nice and straightforward. You simply go through and say, okay, well, as long as there's enough space in A's array, we just take B and copy it at the end there. If we're creating a new string, then obviously we can go through and hopefully allocate something that's big enough and return it. If we're dealing with things like that, then you can get some extra sort of tweaky things that you might want to think about. If you've got operations to go through and calculate the length of a string, right, where a null terminated character array, it's going to have to go through and find the n with a size stored one. It just has to look up that first field and return it. But suppose we've got that kind of an idea where we want to go through and calculate the array of something, or calculate the length of a string as a character array, and somebody says, I want to calculate the length of A concatenated with B. So we could go through and, the obvious simple approach is simply to say, okay, well, you want to calculate the length of concatenating A and B, we'll concatenate A and B and calculate the length. Or, if your compiler is smart enough to recognize certain common operations and shortcuts, then it might say, oh, well, wait a minute. If I take the length of A and the length of B and add them together, I get the same thing, right? They're not actually using the concatenated string anymore. They're just asking how big it is. So maybe I go through and say, okay, well, instead I'll calculate the length of each of them individually, which especially in terms of our null terminated character arrays is going to be faster if I compute the lengths of 2 short strings rather than concatenating them together, which is going to involve, copying all of one of them. It's going to be a quicker operation. So, again, just things to think about in terms of what the compiler might be doing to try and optimize its use of space and its use of time. Let's see, what did I want to look at in terms of structures and records? For the most part, I think we've covered this earlier in terms of sitting down and thinking about what order you're going to stick the fields in. Do you stick with the order that the programmer gave you and pad as necessary to conform to memory alignment rules, or do you rearrange them from sort of most restricted to least restricted in terms of alignment rules? But again, if we've got that covered, then pretty much if somebody comes up with an operation to say, okay, well, I want to look at field S in struct X, then you've got to load the address of X, you've got to load the offset for S within that struct. So here, let's say the offset is 12, then we're loading the 12 into a register, and then you're going through and doing the usual of adding the base and the offset, going off to memory, grabbing whatever's there, and sticking it in a register again. So again, it should be a pretty intuitive operation based on where we've gone so far. But now let's take a look at the idea of, let's say, well, what if we've got an array of structs? So this is something that we do all the time, right? So we've got a student record and we want to represent a class as an array of student records. Or we've got a record for a course and we want to represent all of the courses as an array of these course records. So it's a pretty common idea, and it's pretty common for a programmer to go through and iterate their way through the array looking at a particular field. Iterate through this summing up all of the whatevers, or iterate through it printing out all of the whatevers. So how we choose to implement this can have a significant impact on how quickly things run, depending on what the nature of the actual code happens to be. So again, the obvious solution is to say, well, if the programmer asked for an array of structs, we'll implement it as an array of structs. Right? We know how big a struct is. We'll just create an array of things that size. And if you want to get at, field S in the ith element, then you figure out where the ith element is, and you figure out, the offset to field S, and you go that way. But the compiler might turn around and say, well, the programmer doesn't need to know how it's actually implemented as long as it works the way that they're expecting. So maybe the compiler actually says, well, let's make it so if we've got these three fields, I, j, and k, maybe they're int, char, and float or something like that. Maybe we make an array of the int fields, and we make an array of the char fields and an array of the float fields. And we'll actually implement this overall data structure more as a struct of arrays. And that way, if they are iterating across a specific field, we can do it really efficiently, right? Because all of them are contiguous. So it is certainly something that you can think about, and it's something that, you never know, your compiler might be doing behind the scenes. Just because it looks one way to you doesn't mean it actually works that way under the hood. What else have we got? Unions. That's always a fun beast. So this is the idea that I can say a specific item can be of type A, B, or C. And the compiler says, okay, if it can be any one of those things, but it can't be multiple at one time. It's not like a struct where you've got these separate fields where you're going to store, data in field A and data in field B and data in field C. You're saying at any given instant, it will hold one of these three kinds of data. So the compiler sets aside enough memory space for that item to hold whatever the biggest thing is. So if there's, maybe it can hold a char or an int or a double, then it's going to set enough space for a double to fit in. And if you happen to have a char in it right now or an int in it right now, you're probably not using all the space. So you can create these unions, define your unions, and then when you're accessing your variable, you basically just say, okay, well, for variable x right now, for instance, I want to use it as an int. So you specify the integer field and stick whatever value there, or read the value that's there. Or you decide, okay, well, right now I want to use it as a float, so I'll stick a float in there. It does have some nasty implications in terms of type checking, because maybe I go through and assign a value as a float. So right now, it's got the floating point value 1.23 stored in there. But a moment later, you go to look at it as if it holds an int. So it takes whatever binary sequence is in there right now that represents 1.23 as a float, and it reads it as the binary sequence for some integer, whatever that might be. So this kind of thing messes with type checking to no end, but it's certainly something to be aware of. And I just wanted to come back and hash the idea of ambiguity one more time about pointers. So again, if we've got why did I call it a cold memory address? I don't know. I suspect that's an autocorrect, but I have no idea what was it intended to be. However, it was probably going to hold a memory address or reference. There we are. So the idea is we've got pointers that are, either holding a memory address or holding some kind of a reference to a memory location. If we're going through and storing our data values in registers as much as possible, then this really complicates the compiler's ability to tell whether two different registers are actually right now referring to the same thing or not. So if we've got a pointer x and a pointer y, and we've got some regular old variable z, if the value that x points at is in one register, and the value that y points at is in another register, and the value that z points at is in another register, or maybe even we've got a value that y plus 600 points at stored in a register someplace, how do we know that they're not all referring to z, for instance? So you could go through and do comparisons to say, well, is y plus 600 equal to z? Or is, y equal to z, or is x equal to z? But you're talking about adding a whole bunch of extra checks here to figure out whether or not they refer to the same thing. So if, for instance, we don't know whether they all refer to the same thing, and I do something to z, then in theory that might be changing or should be changing the value of the what x is pointing at and what y is pointing at, because they're supposed to be pointing at z maybe. So it introduces this layer of ambiguity that the compiler has to account for. So if you've got pointers all over the place, then the compiler has to say, well, geez, I can't trust that, this thing, might be pointing at this other variable that I've got. I better put it back in memory sort of before and after use. So it does introduce this level of ambiguity that makes using registers effectively much more complicated. Again, the compiler has to take the sort of safe conservative approach to these things. So it is something to keep in mind that the use of pointers does tend to increase the ambiguity from the compiler's point of view and makes it tougher for it to optimize its use of registers. All right, I will leave it there for now. Next week we'll get into iteration maybe a little bit.